Now let's start the second part of today's lecture. We introduced store just before the first break. So now you should be able to expect a change in the type of the intra function. Now the intra function takes an expression to evaluate an environment that contains values of the names that are free in this expression and a store. So this version, we call it implementing boxes without state. Implementing boxes without boxes. State, boxes, memory, that's just the same thing. And now the value is num v, closure v, or box v. In the previous version, we had var here, right? But now it's just an address. Previously, I'm going to show you how it looked like in the next slide. But previously, there was a value. The box v contained the value itself that can change. And that's why the field should be a variable in that version. But now we are gonna implement boxes without using boxes, memory, mutation, state, whatever you call that. It's gonna be pure. It's gonna be purely functional. Meaning we are not gonna use mutation. We are gonna implement mutation without using mutation. Then this intra function will take an expression, an environment, and a store and produces a value and a store. Ooh, that's a big change, right? Let's review one more time. In the previous implementation, just before the first break, box v contained the value itself. Because box contains a value, this box v contains the value itself. So this value can change. That's what we mean by boxes, right? So that's why it's a variable. Box v, when we change the value of the box, then it changes the value it contains. So it's simple, but it doesn't say anything about implementing boxes. So we are gonna take a slightly more difficult track, meaning implementing boxes without using boxes. So box v now contains address instead of a value itself. And the inter function will take an initial store and then produce a resulting store, meaning that before evaluating this expression, it has an environment and a store. Under this environment and store, given this environment and store, we are going to evaluate this expression, which evaluates to this value and may change the given store to this one. Do you see that? One more time. This inter function will take an expression, an environment, and some store, memory. It's gonna result in some value and resulting store. Meaning that under this environment and in this store, when we evaluate this expression, it's gonna produce this value. But while evaluating this expression, we may change this store to this one. Meaning that while evaluating this expression, we may not change this store and just return the same store. So later, not today, but later when we talk about the operation semantics of this PFAE, it's gonna look like this. Under this environment, under this store, when we evaluate this expression, it's gonna result in a value and another store. This store and this store may be different. Okay? So let's implement that. New box. We are constructing a new box, right? Box. The concrete syntax of this introduction of the box is what? Box, open, E. That's the concrete syntax. And in abstract syntax, the name of the construct is new box with E. What's the semantics of this expression? Box, open, E, close. It's gonna evaluate this expression, get its value, and then construct a new box V that contains this value. Really? But you know, box V does not have a value in it. Box V has an address. And store was what? Store was a map from addresses to values. Then what can we do? When we have this box E, what's going to be the semantics? So we are going to interpret this expression and get its value V. But when we construct box V, we need to have an address. Where are we going to get the address? And what's going to be this address for? When we go to that address, it should have this value V. And that should be in the resulting store. One more time. For a given environment and a given store, when we interpret this expression, we can produce another value and the store may be changed. Meaning that under a given environment and a given store, when we interpret this expression, we are gonna make box V with some address, and we need to put this information that in that address, we are gonna have that value. Is it clear? Do you see that? So when we evaluate this expression, the result is gonna be a pair of a value and a store. So interpreting this sub-expression E under this given environment and a store is gonna be a pair of the value of E and a possibly changed store. So I will say multiple times like possibly changed store. Okay, meaning that this S may be just the same with this store or not. If evaluating E did not change this store, this S is going to be the same. If evaluating E changed this store, then this is gonna be different from this store. Okay, because we don't know that. We were just saying that interpreting E will result in a value and some store. Then what's next? I already told you that we need an address, right? We need a new address. Where do you get it? In C. You call this library function called malloc, memory allocation. You should have taken the system programming course, right? And you should know what malloc is. And in this course, we are going to make a very simple, stupid malloc function. This malloc function takes a store and returns a new address. It takes a store, the resulting store, not the input store, right? Because this is given store and this S is possibly changed store. And from that store, we are going to get a new free available address by using this malloc function. And we're going to implement that in a minute. When we have that address, the result is going to be box V with this new fresh address. And we are going to extend this resulting store with this new information saying this new address has this value V. What does that mean again? When we have box open E close, we are saying, hey, I'm allocating a new cell. I'm allocating a new location to the memory. So I'm gonna make a new cell. So give me a new address in your memory. Yeah, it's like that. And you may use this part and that part like that. Yeah, and hey, I need a new address. Give me a free address by asking malloc. And memory allocation system will give you a free space and get its address A and give it back to you. Then what's the result of evaluating this expression? It's going to be a pair. It's going to be a pair. And the first thing is going to be value box V with this new address A. And what's going to be the second thing? That's the changed store. On top of this on top of this resulting store from evaluating this sub-expression, we are going to extend that with what? In this address A, yeah, the value is going to be the value of EV. Meaning that later, when you look up this box, when you want to either get the value inside the box or change the value inside the box, you need to get this address, right? And then using the address, you go look up the store, the memory, and get the value in it. So far so good? Then let's implement the malloc function. Malloc function takes a store and gives you an address back. So malloc function takes a store and then what's the store again? It's a map from addresses to values. So we say, hey, you store, give me your maximum address. And then we're going to add 1 to it. Because this is the maximum address in the given store. If we add 1 to that maximum value, then it's going to be a new one. It's going to be free. So this malloc function is really stupid. It may have some memory leaks, but we don't care. We have infinite memory in this imaginary world. And how do we get this max address of a given store? Max address, again, takes a store and gives you the maximum address in this store. How do we do that? Because we know that this store is a map from addresses to values. We use the KAIST function, KAIST methods on this map data structure. Hey, you, store, I know you are, a map, and give me the set of keys in your map, and then give me the maximum. Okay, so the actual implementation is not that important. All you need to know is that we have this version of memory allocation function, and by using that, we can get a new address and implement the semantics of a new box in this way. Okay. And another way of implementing the previous version is to have just one method by using fold left. This is the Scala implementation and Scala thing. You can either use this version using an auxiliary function or have one function malloc using this fold left function. So I'm gonna leave this function definition to you, and you the better understand this implementation. Again, actual implementation of the malloc function is not really important. That the main thing is just, it's a Scala function that's going to help us to manipulate memory, the store. The second language construct for boxes is open box, meaning what? In that concrete syntax, it was what? E.get, right? It had this one sub-expression, dot get, getter, etc. So getter meaning give me the value in this box. So the semantics is when we evaluate this expression, we'd better have a box V, not non V, but not non V nor closure V, but box V. So when we evaluate this expression, we want to have a box V, and then we'd like to get the value in that address. Now, what can we do? We need to evaluate this expression, right? That's gonna be the first thing. When we interpret this expression B under this given environment and a store, what do we expect? What do we expect? We expect to have a pair. So when we interpret that sub-expression B under this given environment and a store, we are going to have the value of this expression and a possibly changed store. As I said before, this BV, the value of B should be what? Box V. If it's not box V, then this is going to be either num V or clear V. How do you know that? That's how we implemented the value in this language. Then it's going to be an error. I said open box, but the value of B is not a box. Okay, then when it's actually box, what do we expect? What do you want to do? When we interpreted this expression, we got box V, which has an address. Do you want to get an address? No. We want to know the value at that address. What's the address? That's an integer, right? What's the store? That's a map from addresses to values. Meaning that using this address, we need to go look up this store, yeah? And then, hey store, at this address, what do you have? That's what we want. So, what do you think? We need to have a function to look up the store. Do you see that? Are you with me? Let me explain that one more time. When we evaluate this expression B, we expect to have a box V value. And box V has an address. When you have an address, what do? You go to that address. It's like a postman. When you have a letter and you'd like to deliver the letter to this address, then what do? You need to go to that address and knock the door. So we need to look up the store and then ask what's in that address. That's store lookup. Remember, when we interpret an expression ID, how did we get the value of ID? We looked up the value of that name in the environment. What was the environment? It's an environment which is a map from names, right? What did he say? Var, right? Names to values. Because it's a map, we looked up the name from this environment and get the value. What about the store? This store M is store, which is a map from addresses to value. And what is address? It's an integer. Address happen to be an integer, just like number n. Yeah, let's say n is a number and address is an A. Even though they are both numbers, they may be different. I will say more about that in a minute. So when we have an address, we need to look up the store saying, hey, in this possibly changed store, what's the value in that address? Then it's going to give us the value. Then the store didn't change. When we just looked up the value in that box, just looked up the value in that address, the store doesn't change. Just looking up, right? So the store doesn't change, but we need to be able to look up the store using the address. So far, so good. One thing to emphasize is that, as I said before, the number in this language, the num V thingy, and this address, A, they are different things. In this language, when we have addition, it's going to be N1 plus N2. It's not going to be A1 plus A2. It's not allowed in this language. But in C, you know that addresses are just numbers. That's why people like to use C languages? Because you can add numbers to addresses. You can even multiply numbers to addresses, and you can manipulate memory. It sounds cool, but really dangerous. That's why many C programs have errors, right? There is a joke in the programming language community, like if you have a C program, you can find a bug in it. That's the main beast of using C for highly important programs. So later in your midterm exam or in your final exam or whatever problem set that you're gonna encounter later, a new language may be introduced, and in that language we may ask you to allow addition of number and addresses, just like C. So you should be able to do that, but not today. Today, the third language construct for boxes is setting. In concrete syntax, it was E1 dot set E2, right? Meaning that E1 should be a box, E2 should be a new value in that box. One more time, E1 should be box V. It cannot be non-V or closure V. It should be a box V which contains an address. Yeah, that's the definition. So when we look up the store using that address, there should be some value. Why? Because our construction of an address, of a value thingy, always requires our initial value. So we cannot have a location without any value, without any initialized value. So even though it may have some old value, we are going to evaluate the second sub-expression, get the value, and put that in that address. That's set box, right? Then what are we going to do? We are going to interpret the first sub-expression, and we are going to evaluate the second sub-expression, right? It's like B dot set, open, E close. We need to evaluate this and that under the given environment and under the given store. Really? Not really, right? Because we said that evaluating an expression may change the store. So if there are two sub-expressions, then we need to change that. I mean, when we interpret the first sub-expression, it may be okay to use a given store, but it may not be okay to use the same store for the second sub-expression, right? Really? Let's see. When we have this example, what happens? Let's construct a new location initialized to 10, and let's call that box Q. Okay. Then what do we do next? And change the value in that address to 12 and return the changed box. And then we are going to change that box with what? The value in that thing. What is that, right? So when we have this box in the beginning, it's going to contain 10. Okay. But this is just this example. Let me tell you this mapping. Set box BE, meaning we are setting the box B with the value of E. Are you with me? So when we evaluate this B, we are going to use the same environment, the given environment. When we evaluate this E, we are going to use the same given environment. But when we evaluate this B expression, we have no option than using the given store. But how about this? Are we going to use the same given store, or are we going to use the possibly changed store while evaluating this expression? Meaning, when we get the value of Q, are we going to get 10 or 12? Of course 12, right? Because that's what we want. Meaning, we cannot use the same store. Ooh, then what do we want? We will talk about that after the second break.